I'm going to start over. Again, the subject here is length. Length of a curve or a function. So I have some curve, or some function, if you will, and I have a point A, starting point, and a point B, an end point, and I want to know what the length of this is. So to start with, as just a very rough estimate, I can find the delta x, which is b minus a, and the delta y. Well, the delta y is f of b minus f of a. And I could just, as a first estimate, I could just say, for first approximation, use a straight line. So, in this case, the length would be approximately, this is not a very good estimate for many curves, right? I mean, if I have a curve like this, it's going to be a very bad estimate, right? But it's approximately, using Pythagorean theorem, the square root of delta x squared plus delta y squared. And to the degree that this is actually, a small distance, you might note that dy dx times delta x is approximately equal to delta y. It's not very good in this case, but to a very rough estimate, we can estimate delta y this way. So that tells us that L is approximately, all right, so I'm going to plug in for y, delta x, delta dy dx over here. I'll be able to take out a factor of delta x squared out from the root, so it's just delta x times the square root, and here I'm left with 1, and here I'm left with dy dx squared. All right, so as a rough approximation, this isn't very good, but the next step in trying to evaluate what the length might be would be to take this curve and to break it up into pieces. Let's call A x naught, y naught, and B we'll call x to the n, y to the n. And then in between you have x1, y1, x2, y2, all the way up to b. So now I have, instead of one big triangle, I have lots of little triangles. And because they're getting smaller and smaller now as I increase the number of points, the accuracy gets better and better. So again, now my somewhat better approximation is just the sum. And now I'm going to throw some quick notation at you, which you can ask me about. I'm going to say the sum of delta x sub I, where I goes from 1 to n. And delta xi is, it's going to be xi plus 1 minus xi. In other words, just each of these delta x's here. And this again is times the square root of 1 plus dy at x sub I dx squared. So here's the part where it's hard work getting hot. Took off my sweater. And hand wave. Mathematicians always do this in lower level classes. You see that if I keep making n bigger and bigger, in other words, if I let n go to infinity of this sum, I'm just going to end up with the integral, all right? In other words, I'm going to end up with this integral from a to b of square root of 1 plus dy dx at x dx. So this now is my formula for finding the length of some arbitrary function or arbitrary curve. This formula is something you need to know, so if nothing else, put it on your cheat sheet. Okay, let's leave this here. Someone left me a present. Remember what this, we know what this must be? Yeah, it's a normal curve. Probably a statistics class. Could be, yeah, probably. Oh, let me ask you an environmental question. People want that door open? I didn't open it. Okay, I'm going to close it. Okay, so here's a problem. Let's take function x to the 3/2 on the interval 0 to 4. Okay. And we want to know the length of that function. At 0, it's 0. At 4, it's 8. It's kind of a somewhat like a parabola. So we use our formula. We want to find the integral from 0 to 4 of the square root of 1 plus, well, we need to know the derivative. So what's f prime of x? Just 3/2 x to the 1/2. So this is 3/2 x to the 1/2 squared dx, which simplifies to square root of 1 plus 9/4 x. This looks awfully familiar. Looks a little like a problem I had on the midterm. Not on the midterm, on the quiz. All right, well, this is an obvious substitution. u equals 1 plus 9/4 x. So du equals 9/4 du dx. Thank you. Or dx equals 4/9 du. We can substitute that in now. 0 goes to 1. Plug 0 in here, and that's what my u is, or my limit. 1 goes in, and we get what? You know, I'm only staring because I thought I changed this problem. Change this problem. Yeah. Change it to 4. There we go. Okay, so I plug 4 in, I get 10. Okay. Square root of u times, here I insert this, 4/9 du. And the antiderivative of x to the half is, or u to the half is u to the 3/2 divided by 1/2, which just multiplies it by 2. We still have the 4/9. And we have to evaluate this from 1 to 10. Okay. So this gives us, this is 8/9, right? Times 10 to the 3/2 minus 1. Okay, that's enough simplification. Unless you happen to know the square root of 1,000. All right, that's just how it works. Any questions about that? Okay, we're gonna try another problem. There's a little message with this problem. There's a message I've been giving you from the beginning, which is sometimes in math you have to be brave, especially on a test or a quiz. You have to say, first of all, I'm confident I can do this and it's going to come out right? No matter what it looks like. So here we have the function 2e to the x plus 1/8 e to the minus x. And we want to evaluate it from x equals 0 to log of 2. All right? This looks like it's going to be trouble, but first we find the derivative. That's pretty easy. Okay, everyone see that? And we're going to look at this is squared. Well, should be able to follow this. It's the first part squared. 2x times 2 times the product of these two. Well, e to the x and e to the minus x cancel. So 2 times an 8 times 2 is 4/8, or minus a half, plus this squared, which is e to the minus 2x over 64. Well, this is getting a little scary, but forge forward. So we plug this into our formula, 0 to the log of 2 of square root of 1 plus 4e to the 2x minus a half plus e to the minus 2x over 64. Well, depending upon the way you look at it, this is either the ugliest thing you've ever seen, or maybe there's something we can do that's nice. Like 1 plus a half, 1 minus a half is just a half. Well, this looks a lot like something we saw earlier, doesn't it? Looks a lot like this, which was the square of this. Yeah, this is just square root of 2e to the x plus e to the x over 8 squared. If you don't panic, sometimes, not always, sometimes things work out. So this just becomes the log, the integral of 0 to the log of 2 of 2e to the x plus e to the x over 8 dx. Now we have to find the antiderivative, 2e to the x plus e to the x over 8 from 0 to the log of 2. Oh, I keep forgetting the minus sign. There we go. All right, well, it's good to know that e to the log of x is equal to x, and e to the log of, to the negative log of x is 1 over x, right? So here we're just going to have 2 times 2 plus 1 over 2 times 1 over 8, 1/16, minus, well, e to the 0 is 1, so 2 plus 1/8. So 4 minus 2 is 2, and 1/16 minus an 8 is minus a 16th. So that's 32, 31/16. Okay? All right. There's one. Questions about this? Everybody okay with this? And it's just we're just applying a formula, and we're using all that good calculus we know up till now to make it work. All right. One more example, and then I'm going to try a few. You will try a few. This one is particularly ugly looking in many ways. We're going to take, and don't panic, we're going to take the log, the log of x plus the square root of x squared minus 1 in the interval from 1 to the square root of 2. Now, before we get going with this, there's something to be concerned about. Let's find the derivative here. Okay, so the log of something is 1 over that times, using the chain rule, times the derivative. So 1 plus the derivative of the square root of x squared minus 1. That's x squared minus 1 to the 1/2. So it's 1/2 x squared minus 1 to the negative 1/2 times the derivative of x squared minus 1, 2x, so that cancels. And let me simplify a little here. X squared minus 1 plus x, square root of x squared minus 1, over x plus square root of x squared minus 1. Oh, these are the same, so this is really square root of 1 over x squared minus 1. I wanted to show you that because as the derivative gets close to 1, as x gets close to 1, what happens to the derivative?
Becomes undefined. It becomes undefined.
It becomes, yeah, it goes to infinity. What this curve looks like is something like this, where if you get close enough to 0, your slope gets to really big. So we already see there could be a problem evaluating this. Our whole, the whole basis of this was that we're making these little triangles smaller and smaller, and we're using f of x. But now, in fact, what's going to happen here, you break this up into little triangles. As we break it up smaller and smaller and smaller, yeah, it's true the derivative's going to go to infinity, but the length is not. There's going to be some kind of limit there. But the book still doesn't like this problem this way, because later we're going to see in this class, in the second part, we're going to see how to deal with integrals where something goes to infinity and you need a limit, but we're not ready for that yet. So what they suggest is, we say, well, what if we take this graph and rotate it along y equals x? Right? What do I mean by that? What do you get when you rotate a function around y equals x? You get the inverse. That's right. So they suggest we try and find the inverse. So, okay. That way, instead of going to infinity, the slope will go to 0. So we're going to start off with y equals log of x plus square root of x squared minus 1. And we're going to switch the x and y. Right? So x equals log of y plus square root of y squared minus 1. And we're hoping we can find y. We're hoping we can find this inverse. All right. Well, the obvious first thing to do is raise both of these to e, because then you get e to the x equals y plus square root of y squared minus 1. Well, that's a big headache out of the way. All right, well, we've got this square root here. I guess the obvious thing to do is subtract y from both sides. In algebra, this usually doesn't work because these are separated. But we're going to go forth and hope this will do the trick. Okay, so what's this squared? It's e to the 2x minus 2y e to the x. Remember, we're trying to get y by itself. Right? Plus y squared equals y squared minus 1. A little minor miracle just happened here. We can cancel the y squared. And now we can solve for y. So we put minus 2y e to the x on one side. We're going to get minus 1 minus e to the 2x. And now we're going to divide by minus 2 e to the x. What do we end up with? We end up with y equals these are going to become positive. I just have to write it out. It's negative 1 minus e to the 2x over minus 2 e to the x. So all the minuses go away. The 2 stays on the bottom. This becomes e to the x. This becomes e to the minus x over 2. All right. Does anyone recognize that construction there? Very well-known function. I don't think they cover this in E anymore. If you look through your book, you're going to find it. This is one of my favorite functions. It's the hyperbolic cosine of x. That's what it's called. There's also a function e to the x minus e to the minus x over 2, which is the hyperbolic sine of x. And there's a really interesting deep correspondence that relates, if you look at the cosine of x and the sine of x and relate it to a circle, you can, in the same way, relate these two functions to a hyperbola. Obviously, it's not exactly the same because the cosine and the sine are periodic. These are not periodic. One of the nice features is that the derivative of the hyperbolic cosine of x with respect to x is this hyperbolic sine, and the derivative of the hyperbolic sine of x related with respect to x is the hyperbolic cosine of x. I'm not going to make you remember that, but it's going to come out of using these real easily. So, all right, let's go back to our formula. Since this is an x interval, we have to switch it to a y interval, right? Because now we're going to, instead of integrating along x, we're going to integrate along y. So let's plug this in. Plug in 1. This becomes 0. This becomes 1. The log of 1 is 0. Our interval is going to be 0. And if we plug square root of 2 in, square root of 2 squared is 2. 2 minus 1 is 1. Square root of 1 is 1. So we have the log of 1 plus the square root of 2. So those are our new limits. You don't want to forget changing the limits. And plugging into our formula, it's going to be 1 plus the derivative of e to the x plus e to the minus x over 2 squared. This is really, we're going in the y direction now, but we might as well leave these as x's. We've turned our diagram 90 degrees, so. All right. Derivative of e to the x, derivative of e to the minus x, e to the minus x. So this just becomes e to the x minus e to the minus x over 2 squared. if you notice that right here, you find the derivative of the cosine of x, just like we said, you get hyperbolic sine of x. All right. The next little manipulation is probably going to look familiar from the last example. I'm going to square this. I'm going to get e to the 2x minus 2 plus e to the minus 2x all over 2 plus 2 over 2. That's what 1 is. Right? And now I can just eliminate this by making this a plus. Okay, so wait, hold on. Hold on. I'm about to do something wrong, aren't I? Oh, I forgot something here. This is squared. This is over 4. Okay, now it's going to turn out right. Okay, so 4 plus minus 2 is 2. Let's do a little surgery here. And I think you can see where this is going. Oh, I seem to have run out of where to put it. So this becomes e to the x plus e to the minus x over 2. Oh, does that really buy me anything? I don't know if I actually want to do that. Oh, you know what I forgot? I got my square root. Yeah, thank you. Of course it's going to buy me something. I just square root and the square knock each other out. So 1 plus square root of 2 dx plus e to the minus x over 2 dx. All right, now I have to find the antiderivative. But again, this is the cosine, hyperbolic cosine of x. The antiderivative is just going to be the hyperbolic sine. So e to the x minus e to the minus x over 2 log of plus square root 2. Okay, we're almost done. If I plug in 0, both of these are 1. Well, that's not what I want to do. Plug this in first. So when I plug in the log of something and raise it to e to the x, right, I just get that value, so 1 plus square root of 2, minus, now this is going to be 1 over that quantity, all over 2. When I plug in 0, both of these become 1, so it goes away. Now I have to do a little work here. 1 plus this, I have to put it over a common denominator, right? 1 plus the square root of 2 squared is 1 plus 2 square root of 2 plus 2 minus 1 over 2 times 1 plus the square root of 2. These 1's cancel. And this is, it's just the same thing on the top and the bottom. It's all equal to 1. Yes?
How could the range at the y-axis become log to the 1 plus square root of 2?
Okay, so the original range is from 0, 0 to square root of 2, what? I guess over here. Square root of 2, well, I plug in 0 here, wait, not 0, 1. If I plug in 1 here, into the function, this becomes 0, this becomes 1, and the log of 1 is 0. So that's why I have this 0 here. If I plug in square root of 2 into this function, 2 squared is 2. Square root of 2 squared is 2. 2 minus 1 is 1. Square root of 1 is 1. 1 plus the square root of 2. So that's where I get this from. It's 1 plus the square root of 2. Does that help? Yeah. Okay, I'm sure you're all tired of hearing me. I'm going to give you a worksheet to work on. I've noticed that when I say things, sometimes it kind of goes in one ear and out the other. So I will get your attention as best I can and say, do not do number 3 unless you want to. So if you do number 3 because you want it to. Okay. I'm going to start in the middle this time. Pass these forward. Pass these backwards. I want by the end of this class you guys to be confident enough to say, Mr. Schoenbrun, you didn't show us how to do that. Oh, let's see. This one looks better.
You can petition it.
You can have it.
Yeah, I know.
So I'm gonna do number 2 on the board. With the parametric equation, the formula is slightly different. But you don't have to know this. You just want to know this because, right? The length is the integral dt, where t is the parameter of, a to b, the square root of f dt squared plus dg dt squared, where f and g are, x is f of t and y is g of t. So this is just a beautiful problem where first you find, so f of x is cosine of t plus t sine of t, so you need the derivative. Negative sine of t plus t times cosine of t plus sine of t. Oh, that cancels. That's nice. And g prime of either t. G of t is sine of t minus t cosine of t. So g prime of t is cosine of t minus t times negative sine t plus cosine of t. And of course, these now cancel. So we end up with integral from 0 to pi of this squared, t squared cosine t, square root of t squared cosine squared t plus t squared sine squared t dt. Take out the t squareds. L equals 0 to pi of t times the square root of cosine squared t plus sine squared t dt. But of course, this is just 1. So this becomes t squared over 2, 0 to pi. It just becomes pi squared over 2. And that's number 2, the one I didn't want you to do. You don't have to know that formula. We're not going to, I don't think we're going to do much with parametric equations in class. So. All right. I don't want to go over number 1 because 1 is the same as the problem I did on, first problem I did in class. I'll give you guys a choice. Would you rather I go over 3 or 4? Raise your hand if you want 3. 1, 2, 3, 4, 5, 6. Raise your hand if you want 4. 1, oh, yeah, okay. You guys, you understand voting in America. You just don't go to the polls, right? And then somebody else gets to decide. Okay. Let me do number 3. And then we're almost done with length for today. So we have this function 1/3 x squared plus 2 to the 2/3 on the interval from 0 to 1. So we want to know the derivative of this function. So x squared plus 2 to the 2/3 is going to be 2/3 or 2/9 times x squared plus 2 negative 1/3.
Oh, okay.
Times 2x, thank you. So this becomes 4/9.
Oh my god, like the whole year.
Okay, so now let's plug that into our formula. It's now a dead. Stir it to 1 of the square root 1 plus this whole thing squared. So that's x squared 16 over 81, and then over, well, I'll just leave it this way for now. X squared plus 2 to the negative 2/3. Well, that's ugly. That's really ugly. Guess I will write it that way. Over x squared plus 2 to the 2/3. Well, I want to put this all over a common denominator. So 81 x squared plus 2. Oh, did I square this? Yeah, I did. Plus 2 plus 16 x squared all over 81 x squared plus 2 to the 2/3 dx. Well, we can at least simplify the top, right? X 81x squared plus 162 plus 16x squared, which is 97x squared plus 162 over 8. Did I miss something?
Yeah. 2 over 3. On the top.
Oh! Yeah, I can't do that, can I? Okay. Well, this doesn't look nice. Looks terrible. Well, I could break it up into 2 parts, couldn't I? Oh, no, we still have the square root to deal with, don't we? Well, I'm kind of glad. I mean, I didn't know it was going to be an impossible problem to do exactly. But I like the fact that, you know, when you look at this construct here, square root of 1 plus df dx squared, a lot of the problems we do that come out right are kind of manipulated that way. They'll come out right. But on the average, if you randomly pick some function, it's unlikely we're going to be able to do this, right? So, what's our next best strategy? He says, turning the doc cam back on. I shouldn't have turned it off. Huh? There we go. What's our next best strategy? And an approximate answer. Oh, you're there. Okay. How are we going to do this? Well, what was our original function? I guess this was it, right? Is everyone happy with this as the derivative squared? I don't know if I am yet. Oh. Yeah. Where did this x come from? Oh, right. The chain rule 2x squared. All right. All right. So let's see if we can do this. So the outside is the square root. And then 1 plus 16 x squared divided by 81 times x squared plus 2 raised to the 2/3. Now, if we get a nice, pretty answer out of this, we'll know we missed some. All right? Second calc, 7, 0, 1. That number looks familiar. I'm not sure what it is, actually. I mean, sometimes, you know, you want to divide it by pi to see if that, no. That was multiplied. Wait. There's no undo, is there?
You can just select it by moving the arrow up and then pressing it. Yeah.
I used to know that. Okay, so if I say that,
You can just press enter.
oh, okay. X and Y. Does anyone know where this comes from? The name? Yes. Yes, it comes from the well-known philosopher, mathematician, Rene Descartes. Should be Descartesian coordinates, but that would be much harder to say. But of course, calculus, mathematics, should not depend on the coordinate system. And so we're going to do a little investigation into doing some calculus in another set of coordinates, which you will probably know as polar coordinates. Now, I'm going to do a little review anyway. Is there anyone here who has never heard of polar coordinates? Because I think we do them in high school, and I think we do them in Calc 1A. So the idea in polar coordinates is instead of an XY grid, we have instead coordinates r and theta, where we arbitrarily, you say what we used to call the positive x-axis is theta equals 0, right? So theta is an angle here, and r is the distance from that point. Now, one very, very, very important difference, polar coordinates and Cartesian coordinates, is that polar coordinates are not unique. So, for example, let's say pi over 2, 5. That's the same as 5 pi over 2, 5. But it's also the same as 3 pi over 2, negative 5. In fact, there's an infinite number of ways to describe each point. Sometimes we have to be careful with that. The worst case is 0. Like, you know, you can put any 0 degree, I'm sorry. The worst case is r equals 0. Then you can put in any theta you want, and they're all the same point.
But the color, but you write the R for
The first one, you write R theta and
Thank you. R. Okay. There we go. Thank you.
but you write the
Did I get it right this
No,
time?
what they're saying is like on your example for polar coordinates, it says r comma theta,
Yeah.
like the black part.
Oh, but I'm writing them the other way, aren't
Yeah.
I?
that part.
Yeah, it should be r theta, sorry. I don't use polar coordinates enough, that's my problem. Okay, now I've got it right. I think. Okay, so first thing we want to know when we're dealing with these coordinates is how to convert them back and forth to Cartesian coordinates. This is quite straightforward. If you have a point r theta, you want to convert it to x and y coordinates. X equals r cosine theta, y equals r sine theta. All we have to do is draw a little triangle here, and you can see that this is r sine theta, this is r cosine theta. So our coordinate here is r cosine theta, r sine theta. And that gives you a unique x and y. The opposite direction isn't quite so nice. If I want to go from xy to r theta, well, r, we just use the Pythagorean theorem. But theta is the inverse tangent of y over x. Unless x is equal to 0, so x can't be equal to 0. If x happens to be 0, what happens? We have a point on the y-axis. Is that right? What happens then? Well then, theta is equal to either pi over 2 or 3 pi over 2, depending upon whether r is positive or negative. Okay, using the do we know what I mean if I inverse? You know what this difference between these notations is? Just so I'm clear. This is a function, right? So we have to restrict the domain of it. Because tangent is a periodic function, right? So this thing is not a function, and kind of looks like, let's see, right, it doesn't pass the vertical line test, but this is a function, and by restricting the domain, we make this into a function. So using the tangent here, we do get a unique value. That doesn't change the problem with polar coordinates, but it does give us a unique value if we want to convert. Okay. All right. Next thing I want to talk about for a minute is what an equation in polar coordinates might look like. So, I know I'm going to need this in a minute. Let's get this going. So, I said r equals 2. That would be an equation in polar coordinates. What would that be the equation of?
Circle. Circle.
Circle. I go out distance of 2, and then I don't care what theta is, right? All right. How about, anyone have an idea what r cosine of theta might be? Well, for theta 0, cosine is 1. For theta, say, pi over 2, cosine is 0, so those are 2 points. How about pi over 4? It's out here somewhere. Right. That's what? Cosine of pi over 4. Everyone should know this.
Root 2 over 2?
Root 2 over 2? Okay, so I'm going to draw root 2 over 2. That's interesting. This is root 2 over 2, this is root 2 over 2, and this is 1, right? Which is as it should be. Kind of starts to look like another circle. Okay, we're going to have a brief little lesson. If you have your calculator, I encourage you to pull it out now and step along with me here. So let's go to mode. Everyone find your mode. Now, let's go down here. First of all, you should be on radian. You almost always want to be in radian in calculus. I have a story, but okay, I'll tell you a quick little story. So I was teaching high school, and I had this small little calculus class, and I had this student who thought he was smarter than the teacher. I don't mean he thought he was better at math, he just, thought he could get away with something. So he brought a calculator to the final. And it wasn't a TI 83 or 84, it was the next generation up. And you can plug into those calculators a function, and it'll find the exact integral. But he left his calculator in degree mode. So we got all these weird constants which you put on the exam, right? And that was what happened going. So I didn't know what to do actually, because he cheated, although he cheated on something that I hadn't said he couldn't do, and he got them wrong. So just had to mark them wrong. Okay. Down here, func. I don't know what func is supposed to stand for other than function. But you'll notice there's har, which is parametric. If you want to graph something parametrically, we talked a brief bit about that. Here we have pole, as in polar. So hit enter, and now we're in polar mode. Be really careful. Well, you'll know. You'll see why you'll know. If you don't want to be in polar mode, get out of it. But let's go over to Y. Oh, Y. Notice that now it's R equals E, well, some function of theta. Right? If I hit the X button, I don't get X, I get theta. Right? So, all right, what's our function? R equals cosine theta. Let's graph it. Something surely went wrong there. Let's take a look. I put us into polar mode. Did I put us into radian? Okay. Here, the window setting is really important. We want to go from 0 to, let's try 2 pi. This is different from the regular mode, the Cartesian mode, where it's really not going to matter. Why is this giving me the wrong answer? What am I doing wrong? Cosine theta. Should be a circle. I have something set up wrong, and I don't know what it is. Ute. Did anybody get a circle when they did this? Or did everyone get this same strange looking window?
The step should be.
Okay. I wasn't doing it very smoothly. I guess that's what it meant. Thank you. Let's try and make it really smooth. Oh, I see. That's going to just take a long time. Now, you might say, this doesn't really look like a circle. It looks like an ellipse. But that's because my axes are set up differently. And I think if you say zoom square, or there might be other things. Oh, it's busy. Zoom square. Okay, so now we're going to get tiny, teeny, tiny little circle. Now there's something you can see here going on, right? Because it goes around, but it's still busy. That's because it went from here to here, that was pi over 2, and here to here pi, and then it repeated it. I didn't really need to go to 2 pi. So if I say window pi, I'll get the same thing, only a little faster. It's just going to do it once. And actually, if you think about it, the other reason it's going slow is my step is obviously too small. So let's about 5. Oops. Here we go. Except now it's a little rocky. So now here I need a better step. Okay, so you should play around with this a little so you get a feel for polar coordinates and how that works. Okay, here's something that's fun. Who here does not have a calculator with them? Everybody's got one? Great, okay. I want everyone to graph on here r equals 1 plus cosine theta. insert 1 plus, okay. Has everyone seen this already for themselves? Okay. Well, now, I guess I'm just going to do every mistake at least once. So let me zoom out, right? And now you can see that going from 0 all the way over here, actually that was pi, right? So really, again, I want to increase my max to 2 pi. Oops. 2 pi. Okay, this is called a cardioid. Root, card having to do with a heart. If you have a problem with your heart, you go to a cardiologist, right? The math has nothing to do with hearts. It's just that's what it looks like. Okay. All right. How about trying this? R equals cosine of 2 theta. You guys were brought up with calculators. I didn't have a calculator when I went to college. Certainly not one with a little graphic thing on it. Missed out on all the fun. Look at that. What's that? It's a propeller engine or cloverleaf? Okay. Okay, some useful bits of information from the polar coordinate worlds. I guess we need some new way of, we have f of x, right? For a function. I want a polar function, but I don't want to use f. So, what's a nice Greek letter? We'll use alpha of theta, right? So if alpha of theta is equal to alpha of negative theta, in other words, if I have a point here, and I also have a point here, I have a point here, and I also have a point here, a point here, and I also have a point here. What does that tell me about this? It's symmetric about the x-axis. Okay? X-axis. Okay, so this is a symmetry. So, thinking of those equations we just used, certainly r equals 2. Change theta to minus theta. Doesn't change, and the circle certainly symmetric over the x-axis. cosine of r equals cosine of theta, right? That was also a circle, or 1 plus cosine of theta. Since cosine is even, this is going to be equal to this. So anything with just a cosine will be symmetric over the x-axis. On the other hand, if theta alpha of r is equal to alpha of negative r, so what would that look like? So if this is a point, then this is also a point. This is a point, then this is also a point. What kind of symmetry is that?
Inverse.
Inverse. Not sure what that means.
No,
It's symmetry. This is around the x-axis. This is around the
zero.
origin. Yeah. Maybe that's what you meant. I'm not sure. And if alpha of pi minus theta is equal to alpha of theta, okay, what does that look like? So this is some point. It's theta. What's pi minus theta? Well, that's over here, right? This is pi minus theta. Or here, same thing, right? So this is now symmetric around the y-axis. I mention these things because, you know, we found some usefulness to even and odd functions in Cartesian coordinates. Sometimes you can simplify a integration by realizing that, and that may be the same also in polar coordinates. Okay. We only have a few minutes left, but I guess we'll start one more piece, and then we'll begin again on Tuesday. The homework for this section is not due till after the midterm, right? So you can start looking at it if you want, or after Tuesday. So suppose you have some polar function, alpha of theta, and suppose between theta 1 and theta 2 you have some area, and you'd like to calculate what that is. Using calculus, of course. Well, let's look at a little tiny sliver here. Right? We'll call this delta theta, and we'll call this r. So if this is a little tiny sliver, if you think of this as part of a circle, perfectly drawn circle, right? Then the area of the whole circle would be what? No, that would be the circumference. Pi r squared, okay? But this is only delta theta of that circle. So that would be delta theta over 2 pi, right? So simplifying, we have that we call it the delta area is approximately equal to r squared delta theta over 2. Thank you. So it won't surprise you that if we sum up all the delta A's areas, right, and we make delta theta go to d theta, right, and make it very small, that we're going to get an integral of this form: theta 1, theta 2, over 2 r squared, well, we're going to call it alpha, aren't we? Alpha of theta, or alpha of theta is the radius, right? D theta is squared. I don't have time to do an example, but I will on Tuesday. But this is now going to be our area. In polar coordinates, or how we're going to figure it out. Okay, that's it. Thank you all. Do you have any questions or issues? You are dismissed. Theta 1 is theta 2.